So, in my last lecture I discussed this benefits of capacitor placement. I discussed two numerical problems just to illustrate you that what kind of benefits we can get with the capacitor placement. Okay. And at the end of my last lecture I discussed that there are two types of planning process for locating and sizing these capacitors or to determine the capacitor location and sizes. One is you know that investment planning, that is one step procedure, that is basically to find out that what are the optimal location and sizes for capacitor by optimizing certain objectives. Another is of course, that operational planning. Okay. So, which is basically in which you we are supposed to determine that how much compensation we require in a particular instant of a time in a day or particular duration of time in a day. You have seen that our load always varies and we can plot this variation of this load in a load curve. Okay. And that load curve can be 15 minutes load curve or 30 minutes load curve, all these things I discussed. So, with this varying load demand, with this time varying load demand, our capacitor compensation needs to be varying. Okay. Otherwise, what could be the problem? Otherwise, this capacitor compensation under very light load condition, when load demand is very low, but capacitive compensation is very high. At this particular scenario, this may cause harmful this scenario may be harmful to the network, in a sense that this will cause over voltage in the network. Okay. How it will happen, I will show you after a few minutes. Now, so in order to avoid that, we need to determine the time varying compensation that we require for throughout the day, okay, for a particular distribution network. Okay. And this process is called operational planning process. Okay. Of course, this investment planning or the planning process in which we determine the sizes of the capacitor, this is usually done with the peak load demand data. Okay. That means, we determine the capacitor sizes and of course, capacitor locations when considering the fact that the load demand is at peak, okay, or load demand as its highest value. Now, this amount of capacitor size, it is just for the sizing of the capacitor, just to determine the optimal sizes of the capacitor, but that much of capacitor will not certainly keep throughout the day, because this will lead to this procedure is called fixed compensation. So, if you fix the capacitor compensation throughout the day, this will be a problematic when the load demand is low, and this will result in an overcompensation, very huge overcompensation, and that will cause the over voltage, which is not desirable. Okay. Neither this is the objective of this capacitor placement. Okay. So, we need to determine the time varying capacitive compensation we require throughout the day, and that procedure is called operational planning. Okay. Now, here you can see this is in this slide we have an example. We have a typical single feeder distribution network. So, this is a single feeder distribution network, and these arrows, they are showing as usual, they are showing the load. loads of that particular feeder, and these are the different nodes as you can see where this one particular load is located. Okay. Now, without any capacitor, how would be the voltage profile of that particular radial feeder? These things you have seen in my last module, when I talk about this forward backward sweep load flow, and I had shown you the results of this forward backward load flow, forward backward sweep load flow, and this result you can see I had shown the plots of the voltage magnitudes of individual test systems. There you can see that voltage will fall from starting from the substation to the end of this feeder. Okay. Now, this black the characteristics, this characteristics is shown that this is the voltage profile of the network without any capacitor, without any capacitor. So, starting from this substation, voltage will gradually fall, and this how it will fall, it may be linear or non-linear or whatever, that depends upon these types of the load and how they are located, whether they are uniformly distributed or some amount is lumped or what. So, but obviously, this voltage profile will be something like that, it will fall starting from this substation voltage. So, this is our substation voltage, and we keep usually this substation voltage as 1 per unit, we call it 1 per unit. Okay. And if it is 1 per unit, you will see at the end of the feeder, that means at this point of the network, at this point of the network, that means at the location where the distant load is located. So, here you can see there is a, this is the distant node, and at that particular node you will see the lowest voltage, because in subsequent section you can see, in subsequent line you can see there will be voltage drop. So, here there will be voltage drop, here there will be voltage drop, and so on. So, at the end of this feeder you will see the voltage profile is something like that, and the voltage at the distant node is the lowest. Now, there are two dotted line which shows this maximum allowable voltage and minimum allowable voltage. So, you can see this is suppose the minimum allowable voltage of the network. We call, let us say it is we call that 10% voltage drop is acceptable. So, minimum allowable voltage drop is here is 0.9 per unit, okay, and this is the substation voltage which is 1 per unit. So, you can see that at the distant node this voltage is lower than the minimum allowable voltage. So, this voltage is lower than the minimum allowable voltage. Okay. That might be any value lower than 0.9, that might be 0.85, 0.87 or whatever. But at that node the customer who are connected at that node, which is the distant node of that particular feeder, they will experience under voltage, they will experience under voltage. Okay. So, this is basically drawn this voltage profile at rated load, or at peak load, So, this is the voltage profile at peak load demand, okay, rated load or peak load, whatever you can call it. So, this is the voltage profile, this one is the voltage profile at the peak load. Now, suppose in order to alleviate the situation that some of the nodes may suffer from this under voltage. So, we can place a capacitor somewhere in this network, and it is arbitrarily chosen at let us say point A, we will put a capacitor. Okay. And we also select the size of the capacitor such that this voltage profile will be shifted at this point, shifted here like this, and it will bring this node which was suffering from under voltage problem without any capacitive compensation is out of this problem. That means, this is shifted to the this voltage of that particular node is improved or increased to that value, which is within which is even higher than the allowable voltage. So, I can suppose initially that voltage was let us say 0.85 per unit, and with this capacitor placement it increased to 0.92 per unit. So, I can say that with this capacitor placement I improved this voltage of that particular node which was suffering from this under voltage problem to allowable voltage. Okay. And that is what the purpose of the capacitor. Okay. Now, what could happen if this load is reduced to some lower value than this peak load, or load is reduced to the least value throughout the day, because as you know load will vary throughout the day. So, this capacitor size and maybe its location also is decided, this size and location, these are decided based upon the this peak load demand. Okay. Now, what could happen that if we keep this capacitive compensation same at any other loading point other than this peak load demand. So, let us see the another scenario. So, here all these things, everything is same, only thing is that the load demand is reduced to the light load. So, here as compared to the previous scenario everything is same, but load demand is reduced to lowest possible value, So, under this scenario this you know so this was the voltage profile of this network at peak load demand without capacitor or without any compensation, and with at this light load condition this voltage profile will be of course shifted upward like this, voltage will continuously declining and it will be like that, let us say. So, this is the voltage profile at light load condition. Okay. This is also without compensation. Now, with this capacitor, that means by keeping this capacitor compensation fixed, which we obtain from this previous scenario, that is when this load demand was at peak, and at that time what could be the capacitive compensation. So, that we can bring out those nodes from the problem of those nodes who are suffering from this under voltage problem from the under voltage problem. Okay. Now, if we do so, then and if we keep the same amount of compensation even at this light load condition, the characteristics or voltage profile would be something like that. So, here you can see there is a rise in voltage. So, this shows rise in voltage above the substation voltage for the some of the nodes. So, you can see here some of the voltages I mean some of the nodes who are nearby this capacitor who will experience this over voltage problem, okay, due to this fixed capacitor compensation, and that is why capacitive compensation cannot be fixed throughout the day. So, this gives an lesson to the fact that the capacitive compensation capacitive compensation, or I can say the fixed capacitive compensation results in over voltage at light load condition in some nodes. So, some of the customers who are located near to the capacitor, who are experiencing in fact under voltage previously during peak load condition, we will see that they are suffering from over voltage condition due to the fixed capacitor compensation, and therefore, this fixed capacitor compensation cannot be used throughout the day, and we need a varying capacitive compensation. So, this is what I exactly trying to make you understand, that only fixed capacitive compensation or only fixed type capacitor installment will lead to the voltage rise problem during light load condition. Okay. So, therefore, what the utilities used to follow, that they keep some of the capacitors as switched capacitor, because in capacitor banks there are many capacitors which are in series parallel combination, which are connected in a series parallel combination, and some of the capacitors are kept as switched capacitor. It means that they will be used only if these are really required, okay, or only if whenever there is a peak load condition. Okay. So, they will be switched during and they will be switched off during light load condition. So, that at light load condition this degree of capacitive compensation is becomes low. Okay. And there would be of course, some fixed capacitors who will be present throughout the day, okay. Because as you know, capacitor switching is itself a problematic, because it will cause transients in the network, it may cause over voltage. Okay. So, switching of the capacitor is something which the utilities they try to avoid. But even if we keep that all capacitor fixed, that is also a problematic, in the sense that during light load condition, some of the consumers or some of the loads will experience over voltage. So, we have to have a trade off in these two situations, that we have to keep some capacitors fixed, capacitor switch able, but we need to minimize the switching as much as possible. Okay. And this is a typical switching or typical time varying capacitive compensation. So, this gives typical time varying capacitive compensation, and these characteristics is drawn by in this axis, this reactive power, the capacitor is injected to the network, and this is with respect to time, and this time starts from 12 o'clock at the midnight and ends at the 12 o'clock at the next day midnight. So, you see that that during this period, when load is very light up to this period, you can see that only some fixed capacitive compensation will be there throughout the day, and that means up to 600 kVAr So, this shows that up to 600 kVAR would be fixed capacitive compensation. Then rest of the capacitors, whereas this capacitor size is something like 1800 kVAR. So, the size of the capacitor bank, size of the capacitor bank is 1800 kVAR. This is an indicative, this does not mean that means it should be similar for every network, or this is the common practice for all the utilities. So, actually in utilities follow this practice, that some of the capacitors are kept fixed and some of the capacitors are switchable. So, you can see that even though that capacitor bank size is 1800 kVAR, out of which only 30%, one third of that capacitor are kept fixed. Okay. And this is to compensate this base load condition, and rest are switchable. Okay. And you can see that switching is done in stepwise. So, this is stepwise switching, stepwise switching of the variable capacitor, or switched capacitor. And during this peak load time, all the capacitors are brought into this service, and that time this compensation rises to 1800 kVAR. But when this load demand is low, then accordingly that this utility will decide that how much capacitive compensation will require. So, to determine that this stepwise switching characteristics, so this type of stepwise switching characteristics is usually determined through an optimization process, and this is called operational planning. Okay. So, generally many utilities they follow a thumb rule that kVAR they are, in order to decide the size of the capacitors, and here they use that up to 70% of this total feeder reactive load or reactive power demand would be compensated by a capacitor bank. Okay. And that in that capacitor bank, of course, some percentage will be switched capacitor and some percentage will be fixed capacitor. Okay. And some utilities this is a thumb rule, that does not mean that every time it should be 70% only, but it could be any value depending upon the network structure, depending upon the economy of the system, and depending upon many factors. Okay. Now, what are the economic benefits that we will get in a capacitor placement in distribution network? Okay. So, as I have explained in one of the problems last lecture, that due to the placement of this capacitor bank, if you can remember this numerical problem, then this generator can be loaded additionally 150 kilowatt. Okay. So, this is something was shown in my last lecture. Okay. So, it means that due to this capacitor placement and due to this local reactive power compensation, some amount of capacity of the generator is released. Okay. So, same thing is applicable for other, if generator capacity is released, so as the capacity of the transmission line, so as the capacity of the sub transmission line, so as the capacity of the substation. This is a hierarchical process, and all are the sequential block of this power flow. So, due to this capacitor placement, we get released substation capacity, we get reduced energy loss This is already explained because power loss is reduced, so as the energy loss. I will also show you in the next part of this lecture. Also it reduce this voltage drop and consequently improve this voltage profile or voltage regulation. Also it release the capacity of feeder and associated apparatus, and it needs deferral of this capital expenditure due to this upgradation of the system, due to reinforcement of the system, and also this will increase the revenue, because power loss is reduced, energy loss is also subsequently reduced. Okay. Now, in many of the approaches, optimization approaches, as I mentioned in the last lecture, a suitable objective function formulation is done, okay, in order to determine that what could be the possible size of the capacitor, where we locate those capacitor. Okay. And in order to formulate this objective function, one typical objective function formulation is shown over here. This objective shows that whatever benefits we are getting due to this capacitor placement, one is demand reduction, one is energy reduction, another is increase in revenue, they are aggregated and they are and a composite objective function is formulated. Okay. So, under this demand reduction you can see here we have these 4 components which are basically this released capacities of the individual stakeholder, hierarchical stakeholders, which include generator or generation capacity, which include this transmission capacity, distribution substation capacity, and this feeder capacity. Okay. So, their capacity this is the release of the capacity of individual stakeholder. Similarly, this energy reduction is another component of this objective function, and revenue increase could be another component. So, this is a composite objective function, and accordingly one can optimize that objective. So, that it can decide that how much capacitive compensation it will provide, or what should be the size of the capacitor bank. Again, why I am calling it this a capacitor bank, because as I said, it is not a, although in the figure it is shown a single capacitor, although it is in the figure it is shown a single capacitor, but actually it is a capacitor bank, where we have a multiple number of capacitors connected in series parallel fashion, and they are connected to the switches for the switchable capacitor, and for the fixed capacitor they are directly connected, and they kept on they kept into service throughout the day, okay, throughout the year. Now, in next few slides, or the end part or the last part of this module, I will discuss an analytical approach to determine this optimal location of the capacitor. Okay. I will discuss an analytical approach. As I said, this determination of optimal location of the capacitor and the size of the capacitor, and also how many number of capacitor banks that I should install in a particular distribution feeder, those are normally usually determined by formulating an optimization problem and by solving it. Okay. But this approach, analytical approach, will guide you or will improve or will give you some more insights, so that you can utilize this knowledge on further research or analysis. Okay. So, here although this analytical approach is based upon certain assumption, which I will mention time to time. Okay. So, here we consider a distribution feeder that contains a number of line segments, and with a combination of lumped load or concentrated load and uniformly distributed loads. Okay. So, here we assume that some loads in a particular feeder, there are some loads which are lumped, and so there are some loads which are uniformly distributed. Okay. And also in that different line segment of the feeder, we have sectionalizing switches, we have many other compensation devices. So, for the sake of the convenience, we assume that this power loss can be represented with this in phase component of the current and quadrature or out of phase component of the current, which I already mentioned in my first lecture of this module. So, any current it has two component, one component which is in phase of that voltage, that means if your capacitor or any load is connected at the one particular side of a network. So, across this load whatever the voltage will be there. So, in phase component of the current with that voltage is called in phase component, and quadrature component will be the out of phase component. Okay. So, for example, so I can show you, suppose this is that receiving end side and it is a lump load. Okay. And although this feeder is not a lump load completely. So, we have some lump load and some uniformly distributed load. Okay. Now, for a lumped load case which I explained at the very beginning, how can we represent this voltage across this load and current drawn by this load. So, this is suppose voltage across this load, and this is suppose this current which is drawn by this load I L. So, this I L will have two components, one is in phase component, that is this I or I in, another is out of phase component or quadrature component, that is I out. Okay. So, this I n is basically representing in phase component of the current, and I out is basically representing the quadrature component of this load current, which is connected at a point where this voltage is V r. Okay. Now, here this in phase component, since this current is lagging with respect to voltage, because all loads current are lagging only, because loads are usually inductive in nature. So, if we consider this phase angle of this current is phi. So, I n basically equal to I L cos phi. So, this is the in phase component of the current, and I out is equal to I L sin phi. So, this is quadrature component of the current. So, this is quadrature component and this is in phase component. In phase component, or this is out of phase component. Now, here we are concerned about this out of phase component only. Why it is so? I will come to that next slide, I will explain. Okay. We will not consider this in phase component of the current, because we are basically compensating this out of phase component of current through this capacitor installation. Now, if we install a capacitor at this particular loading end, suppose this capacitor is drawing a current which is leading and this is I c, then you can see it does not have any influence of this in phase component of the current, rather it will compensate this out of phase component of the current, because this out of phase and this they are capacitive current, they are cancelling each other. Okay. And this I c will be capacitor current, which will be quadrature with this supply voltage, assuming that capacitor bank is fully ideal, and therefore, it does not have any influence on this reduction of this in phase current. Okay. So, this part is the plot of this current, reactive current, which is also called quadrature current or out of phase current. So, this is out of phase component or quadrature component, quadrature component of load current. Okay. All right. Now, we are concerned about only this out of phase or quadrature component of current, which can be compensated with this capacitor placement or with the capacitive current. So, this I 1 stands for this out of phase component or quadrature component of the current, quadrature component of the load current at the substation end. So, this I 1 is substation at quadrature component. So, I 1 is quadrature component of or out of phase component of substation end load current, and this I 2 is basically this quadrature or out of phase component of the load current at the distant load of this particular feeder. Okay. And we are assuming that this I, as you know, this current will vary throughout this length, and we are assuming that this length of this distribution feeder is 1 per unit. So, we are assuming the length of the feeder is equal to 1 per unit. All right. Now, you can see at the substation end, obviously this load current will be higher. So, its quadrature component would be higher, and at the distant end load current will be at the least value, and so as the quadrature component. Okay. And we can understand this how we can find out these characteristics which shows that this variation of the current. Okay. We assume that it is a linear characteristics. So, assuming linear characteristics, we consider that this I is following this y is equal to m x plus c. Okay. So, at x is equal to 0, this y is equal to that I 1, and at x is equal to L, this y is equal to this I 2. So, at x is equal to 0, y is equal to I 1. So as this c, because if you put this x is equal to 0, you will see y is equal to c, which is equal to I 1. So, c is equal to basically I 1, and at x is equal to L, y is equal to I 2. So, this is equal to your m L plus c, is our I 1. So, m is equal to I 2 minus I 1 by L. Here we consider L is equal to 1 per unit. So, it is equal to I 2 minus I 1, that is it. Okay. So, I can put it here. So, this current I is equal to m is equal to your I 2 minus I 1 multiplied by x, x is written over here, and plus this I 1, or alternatively we can write it as this is equal to I 1 minus I 1 minus I 2 multiplied by x. Okay. So, this is how this quadrature component of the load current will vary from this substation end to the distant node. Okay. Now, here you can understand that why we are taking only the quadrature component of the current, because you can see that I can represent this line losses as I square R losses. So, I square I can be resolved into two components. So, this is in phase component I in, and this is quadrature component I out. Okay. Similarly, with this adding capacitor, we can which is drawing a current I c. Okay. So, what would be this power line losses? So, this is suppose represented by I 1 square R. Okay. So, here this is your again this I n, that is in phase component of the load current, and this is out of phase component of the load current, but with this would be subtracted this I c, because I c and this out of phase component or quadrature component, they will cancel out each other, and the net amount of this quadrature component would be I sin phi minus I c. Okay. So, this is something like that. Now, if we consider that this is the power loss without a capacitor, suppose this is power loss without capacitor, and this is power loss with capacitor. Capacitor means capacitor bank, you can understand, capacitor bank. Okay. Now, if we take the difference of these two, one is power loss with when there was no capacitor bank, and this is the power loss when we have a capacitor bank installed. If we take the difference of this, and suppose this difference is represented by del PLS, where del PS is basically representing this loss reduction due to this capacitor placement. So, if you take the difference of these two, then this in phase component of this power loss would be cancelled out, because there will be no improvement of this in phase of this power loss which occurs due to this in phase component of the load current. Okay. But only in this difference of this power loss term we will have this quadrature component. That means, this loss reduction, suppose it is represented by del PLS, it is only function of the quadrature component. So, we can write over here. So, only out of phase or reactive component of the line current, that is I in sin phi, should be taken into account for the power loss reduction, because power loss reduction, that is del PLS, is only function of this I out or quadrature component of the current, and that is why only quadrature component of the current is considered in the further studies. Now, since we have it is a 3-phase system. So, this we represent this del PLS, that is differential power loss at a distance x, having a differential segment with a length of dx located at the x distance away from the substation, is represented by this equation. Okay. So, here we take a small infinitely small length of dx at a distance x away from the substation, okay. And we are trying to determine that what should be the power loss at this infinitely small line segment. Okay. Then we will integrate this, this is the power loss, and we integrate it with this varying x is equal to 0 to 1, where x is equal to 0 corresponds to the ascending end side, and x is equal to 1 correspond to the at the end of the feeder. So, if we integrate that, then it will give the overall power loss of the feeder, power loss of the feeder, and that is if you do this integration with by, and then if you put this limit x is equal to 0 to 1, then you will get this is coming out to be that. Okay. Where I 1 is basically reactive current or out of phase current or quadrature current, which is out of phase or quadrature component of the load current at the beginning of the feeder segment, that means at substation, or near to the substation. Similarly, I 2 is out of phase component or reactive component, or you can call it as quadrature component of the current, load current at the end of the feeder segment. And R is the resistance of the feeder segment, and X is the reactance. Okay. X is not applicable of course here. Okay. Now, we will see that if we put a single capacitor bank at some point which is x 1 distant away from the substation, how our reactive current component will change. So, this red dotted line was this previous current profile, that means current profile without capacitor bank, So, what would be the change if we put a capacitor bank here? It will draw a capacitive current I c, and this I c will be opposite to this out of phase component of current. So, it will lead a I c current here. Okay. So, this is I c current, and due to that this previously this up from this capacitive component to this up to this point, this track characteristics of the new current profile, which is with capacitor bank. So, this characteristics is with capacitor bank, it will follow this old profile. Okay. But with this I c current, this new current characteristics will be this. So, here this is the new current profile, which is following a new current profile with this capacitor placement. So, due to this capacitive compensation, this reactive current is reduced to an I c amount from here to the substation end, and that is what the advantage of this capacitor placement. You have seen, I explained at the very beginning that with this capacitor placement at some point that much of reactive current or that much of reactive power we need not to bring from the substation. Okay. And that is why from here to here this reactive power flow will also be reduced. Okay. How much it will be reduced? That much the capacitor is providing or injecting reactive power to the network. Okay. And this will be our new profile. So, this will be the with capacitor bank characteristics, with capacitor bank, with capacitor bank. All right. Now, what we will do? This is our characteristics, current reactive power characteristics, which is from 0 to x is equal to 0 to x is equal to x 1, and this is our characteristics, which is from x is equal to x 1 to x is equal to 1. That is the length of the feeder, that is we consider it as 1 per unit. Okay. So, we will have two current characteristics, one is here to here, another is here to here. So, in order to determine this power loss, we need to consider these two characteristics separately. So, which is done over this here. So, from x is equal to 0 to x 1, we will follow these characteristics, which is with capacitor, this is with capacitor bank, and from x is equal to x 1 to x is equal to 1, we will follow with old characteristics, that is without capacitor bank, and we integrate this as we did previously. We will get P L S dash is equal to that expression. If you do this integration, you will get that characteristic. So, this part will be as usual previous expression, that is this part, and this part is the additional expression. Now, what we will do? We will take this difference of this P L S dash, which is that power loss due to the capacitor bank placement at distance x 1 from the substation. Another is power loss without this capacitor bank, okay, without this capacitor bank, and we will take this ratio of this power loss reduction with respect to this power loss without this capacitor bank. So, this is basically you can write it as a ratio of power loss reduction due to capacitor placement with respect to power loss without capacitor. So, this is the ratio, and you can see that this part is basically eliminated, because this is common and this part will remain, okay, and this is divided by this power loss without capacitor. So, if you simplify this, then you will get del PLS is coming out to be this expression. Okay. So, you can verify whether it is true or not. So, here we purposefully make two ratios, one is I 2 by I 1, another is I c by I 1. So, we get two ratios here, and this del PLS is brought out to be function of these two ratios, and of course, this will be the function of x 1 as well, where x 1 is the location where we put this capacitor. Okay. Now, why we put these two ratios, what is the significance? Because you see that this ratio I c by I 1 is named, it is represented by a variable c, small c, and it is representing that kVA of the capacitor bank to the reactive load of the system, where I 1 is the total reactive load of the system, because it is the reactive component of the load current at near to the substation, where through which all the load currents are flowing. So, this small c is the ratio of the capacitive kVA to the total reactive load. Okay. Of course, it is reactive load, because it is only the out of phase component of the current, load current, and this ratio I 2 by I 1, where you can remember this I 2 is basically reactive current or out of phase component of the current at the end node, and I 1 is the reactive current or out of phase component of the current or quadrature component of the current at the substation end. Okay. So, if you take this ratio, what it will signify? This ratio is represented with a variable lambda, and it is representing the ratio of reactive current at the end of the line segment and to the reactive current at the beginning of the line segment. Okay. So, it has some significance, I will come to that. Now, we represent this del PLS, that is per unit loss reduction, as a function of these two ratios, that is C and lambda, and we get this. Okay. And again we represent 1 upon this 1 upon 1 plus lambda square is equal to variable alpha, and we further reduce this expression like this, which is representing per unit loss reduction. Okay. Now, what we will be doing? We will plot these characteristics. We will plot these characteristics by varying this lambda and c. Here we have as you can see, this is function of lambda c as well as x 1. So, we will vary this lambda and c and plot these characteristics. Okay. All right. Because rest of this thing, even alpha is also function of lambda, and so this is this particular expression is only function of a lambda and c. Now, by varying lambda and c, we will vary the characteristics. So, here what we will do, we consider a single capacitor bank, because this expression is applicable only for a single capacitor bank placement at a distance x 1 from the substation. Now, if we consider lambda is equal to 0 and if we plot c, then what could be the characteristics? So, that characteristics is plotted over here. Okay. Now, what this lambda is equal to 0 actually represent? What this lambda is equal to 0? So, lambda is equal to 0 means, if you look at lambda is equal to 0 means, lambda is equal to 0 correspond to I 2 is equal to 0. That means, this reactive component of the current or out of phase component of the load current at the end of this figure segment is 0. When it is possible? When these loads are only uniformly distributed. Okay. So, this is I explained in module 2 and you can understand. So, that means, lambda is equal to 0 correspond to the fact that line loads are of uniformly distributed. Now, at that particular condition, if we vary C, okay, if we vary C, then how would be the variation of per unit loss reduction? Okay. So, here you can see. So, this correspond to C is equal to 0.1, this correspond to C is equal to 0.2, these characteristics correspond to C is equal to 0.1, these characteristics correspond to C is equal to 0.2 and then C is equal to 0.3, C is equal to 0.4 here, C is equal to 0.5. So, if we increase C, then this loss reduction is getting increased. And now, C is what? C is our degree of capacitive compensation, because C represent this ratio of capacitive kVA to the load reactive kVA. So, C is basically representing degree of capacitive compensation. Okay. So, if C is equal to 0, that means it is the case when there is no compensation, and if C is equal to 1, that means you are providing 100% compensation, that means 100% reactive power is compensated. Okay. So, if you can see, if C is increased, that loss reduction will also increase up to a certain value when C is equal to 0.5. Then you can see the peak loss reduction after C is equal to 0.5 or C is equal to 0.6 will not change, rather only this characteristics is the location where this peak loss reduction will take place is shifted to that side. Okay. So, at C is equal to 0.1, so at the end of this feeder we will get the if we put a capacitor, then we will get highest amount of loss reduction. Similarly, at C is equal to 0.2, it is also near to the end of the feeder. If we put a capacitor bank, we will get maximum loss reduction, but and this holds for C is equal to 0.3, C is equal to 0.4, C is equal to 0.5 and so. But when C is equal to 0.6, C is equal to 0.7, then you can see this peak loss reduction is almost same, but where if you put this, because this axis is representing your capacitor location x1 location. So, if that means higher value of C means that this you should place this capacitor much before this end of the feeder, much before the end of the feeder. For example, at C is equal to 0.7, you can see this is the characteristics. So, that this means that if you put capacitor at a location which is 60% away from the substation or 65% away from the substation, we will get the peak loss reduction. Okay. Now, next characteristics correspond to lambda is equal to 1 by 4. So, when lambda is increasing starting from 0 to any value, that means you have certain amount of loads which are lumped load and certain amount loads are uniformly distributed. Okay, and that is why lambda is non-zero, and it means that out of all this load, certain loads are of lumped and certain loads are uniformly distributed. Under this, how would be the change in the characteristics? You can see if you increase C, this peak loss reduction is increasing, and only thing is that at C is equal to 0.6 and 0.7 and 0.8, this location of the capacitor are not at the end of the feeder, or it should be in between 70% length of the feeder or at 80% length of the feeder. So, characteristics is similar to the previous thing, only thing is that you can see if you compare these characteristics with previous characteristics, the location of the capacitor is getting changed. Okay. So, location is means location of capacitor for peak loss reduction is towards the end of the feeder. Okay. Now, if we further increase this lambda, you can see again this location of this capacitor in order to have this peak loss reduction is at the end of the feeder. Okay. Because again increase in lambda means the amount of the load which are lumped, they are increasing. Okay. Then lambda is equal to 3 by 4 you can see almost linear characteristics, and the highest value of loss reduction will take place if you put this capacitor at the end of the feeder. Again lambda is equal to 1 means it corresponds to this lumped load, that means current characteristics will be flat. If lambda is equal to 1 means I 2 is equal to I 1, lambda is equal to 1 means I 2 is equal to I 1, it means it is a completely lumped load. All loads are concentrated at the end of the feeder. So, where will be the capacitor location, so that we get highest value of power loss reduction we get at the end of the feeder. So, if lambda is increasing, that means we are slowly moving from this uniformly distributed load to the lump load, which are concentrated at the end of the feeder. So, capacitor location would be at the end of the feeder, so that we can get highest benefit in terms of power loss reduction. Okay. So, here some numerical, this table provides you some numerical value for optimum for determination of optimal location and optimum loss reduction, and this I believe that this correspond to lambda is equal to 0. Okay. And you can see that you can get a maximum loss reduction if you place this capacitor at this 0.65, or that is almost 2/3 distance of that particular feeder from the substation. Now, we will talk about the case with 2 capacitor banks. We will talk about the case with 2 capacitor banks. So, if we have 2 capacitor banks which are located at x 1 and x 2 distance, x 1 and x 2 distances from the substation, then how much loss reduction we will get. Now, it means that again you can understand that then how would be that current profile. So, you can see if I go back to this figure. So, here we have one capacitor bank placement. So, if we have another capacitor bank placement suppose at here, then these characteristics will be something like this, and so on. So, if we so this is basically for 2 capacitor banks, at one is located at x 1, another is located at x 2, let us say. So, this is x 1 and this is x 2, and this will be then the current profile for 2 capacitor bank placement, 2 capacitor bank placement, okay, and so on. So, if we have more number of capacitor banks, accordingly that many steps we will be having in this particular characteristics. So, for these 2 capacitor banks, so our expression for this, we will be having 3 segments we have seen, one from x is equal to 0 to x 1, another is from x 1 to x 2, another is x 2 to 1. So, this is correspond to without capacitor, this is correspond to 1 capacitor, and this is correspond to 2 capacitor. That is why it is subtracted 2 I c. Okay. So, if you solve this, you will be having this relation, Okay. So, if we have 3 capacitor banks, you can see where which are located at x 1, x 2 and x 3, you will be having this relation. Okay. Now, we can generalize this. If we have n capacitor banks from this previous 2 expressions, you can find out the expressions for loss reduction, and that generalized expression is coming out to be this, where x I are basically the location of the capacitors, x 1 is the location of the first capacitor, x 2 is the location of the second capacitor, and this will be up to x n, where x n is representing the location of nth capacitor. Okay. And other than that it is essentially same, that means this is function of lambda c and this x I. Okay. Now, one thing that you can observe from these characteristics here, that this load reduction expression has some components. One is this component, another is this component, another is this component. So, this component, so if we write it as a component f, and then if it is f 1, f 2 and component f 3, then you can see this component is a function of x 1 only. Apart from that, it as usual function of lambda and c. Similarly, this component is only function of x 2, apart from that lambda and c, and this component is having it is a function of x 3 apart from lambda and c. Okay. So, this is something is you can understand, and so we can easily determine that what should be that x optimal by differentiating this expression with x 1 and equals to 0. So, we get this is the value of x 1 optimal. So, at that if x I is equal to 1, then it will give you the location of the first capacitor bank or only capacitor bank which will be placed. If I is equal to 2, it corresponds to the second capacitor bank location and so on. Okay. Now, if you put this expression over here, then you will get this optimal loss reduction expression, which is coming out to be this. And if you simplify with, there are many infinite series. So, if you simplify this, then it is coming out to be this expression, okay, which gives you the algebraic expression for loss reduction when we have n number of capacitor banks in a feeder. Okay. N number of capacitors in a feeder. So, it is as usual function of n, it is function of lambda and c as well. Now, we will only study when this capacitor n is equal to 1, that means when this capacitor bank, when we will only use one capacitor bank. So, if you put n is equal to 1 in this expression as well, then you will be getting the location and optimal power loss for that particular feeder. So, if you put n is equal to 1, this gives to this. Okay. Now, differentiating this with c, that means this is a function of now only lambda and c. So, differentiating with respect to c gives you that optimal value of c, that optimal value of compensation you require to get this least power or highest power loss reduction, and this happens to be at x 1 is equal to this. So, x 1 gives you the capacitor location. So, this is capacitor bank location, and this c gives that size, capacitor bank size. Okay. So, if you put these two over this expression, so you will get del PLS is coming out to be 8 by 9 multiplied by alpha divided by 1 minus lambda. Now, if we consider lambda is equal to 0, that means it is a kind of uniformly distributed load throughout the feeder, then alpha which is equal to 1 plus lambda square, you can see, and alpha which is equal to 1 divided by 1 plus lambda square. So, when lambda is equal to 0, alpha will be equal to 1. Okay. So, if you put this two values over here, so alpha is equal to 1, lambda is equal to 0. So, del PLS will be equal to 8 by 9 per unit. So, this gives that much of power loss reduction is possible, which is almost is equal to 88%, 88 point some percent. Okay. Loss reduction of is possible if you put this capacitors, because this part will be equal to 1. So, if you put this capacitor at 2/3 of the distance, 2/3 at the length of the feeder, and if your capacitor size is 2/3 per unit of the total reactive power demand of the network, and this is called the well known 2/3 thumb rule of the capacitor placement, and many utilities they follow this. Okay. So, they used to place a capacitor, if one capacitor bank is to be placed, they used to place a capacitor at 2/3 distance of the 2/3 length of the feeder, and by keeping its size of the 2/3 of the total reactive power demand of the feeder. So, with this they get highest amount of loss reduction. Okay. And without if someone is blind about where to place this capacitor and what should be the size of the capacitor, they follow this thumb rule. Okay. And this is well known 2/3 thumb rule for capacitor placement. So, with this I will stop, and I sincerely acknowledge this materials taken from this Turan Gonen's book on electric power distribution system engineering. Okay. Thank you very much for attending this lecture.